All right, welcome to day 4 of CEDAR. I'm Nathaniel Frizzell, one of the people on the CEDAR Science Steering Committee, and it is my pleasure to welcome Erin Lay up to the podium, and you are going to present the poster awards, right? Wonderful, thank you.
See if I can do it right. Okay. Oh, yeah.
There's also the screen right here.
Yeah, right, but I just wanted to make sure it's up there. Is it up there on the big screen? Yes. Okay. Okay. So thank you everyone for participating in the poster competition. We had a lot of great posters and a lot of great judges, and they made it all possible. And so I'd like to announce the winners of this year's poster competition. I'd also like to mention we had to have 52 judges to make this work. So thank you all to the judges, and if you're invited to judge, which is pretty much all the community other than the students, please take the opportunity in the future. And this maintains our 36-year tradition of supporting the students in our community. Okay, so the first prizes are from the Tuesday poster competition. And for each one, we have a first prize, a second prize, and the honorable mention. So, what's that? And an undergrad award. So, for this year's honorable mention for the Tuesday MLT session, we have Deepali Agarwal from Clemson University. If you would come on up, please. Come on up here. If you would stay up here over on the side for me. Let's see the arrows. Okay, for second place, we have An Fan from Utah State. Oh, there is a staircase over there.
Oh, thank you.
And for first place in the MLT competition, we have Mukta Nyogi from Clemson. Yeah. Please just stay up here for a minute. And now for our undergrad awards. These brave undergrads are willing to present their work to this community of scientists. We have Anthony Zumpano from University of Alaska Fairbanks. Who may not be here today. Oh,
yay.
Okay. Hopefully.
Yeah, that's him. Yeah, that's him.
Did I go the wrong way?
Yeah.
There you go.
Excellent. So now we're going to go to the Wednesday competition winner, And in total, we had for Tuesday and Wednesday, 62 students competing. So this is a very competitive award. The students were fantastic. The work for the judges was very hard. So if you can clap even more energetic, I know it's 8 a.m., but these students work hard. So for the Wednesday competition, the honorable mention goes to Charlie Uga from the University of Alabama in Huntsville. Too tired after the poster competition yesterday, see? They work hard. The second place for the poster competition on Wednesday goes to Austin Coleman from CU Boulder. Yeah, I know. And the first place goes to Bjorn Bergson from Embry-Riddle Aeronautical University. Yeah. And as Erin mentioned, our brave undergraduate students do a fantastic job. And for the Wednesday competition, the undergraduate winner is Anthony Abubakar from the University of Texas at Dallas. Sorry if I mispronounced that.
That's not the right photo. Yeah, that might be a wrong picture.
Sorry.
It is okay.
I'm sorry.
It's my grad bench, it's close enough.
Okay. He looked a bit old, too.
Congratulations.
So last but not least, for all the students, you're going to get the feedback via email next week sometime. So congratulations to all of you.
And if all the students could go down in the front here to get a group photo. And I would also like to thank the tireless efforts of Bea Delacourt. So she worked really hard to make this poster session really smooth this year.
Okay, and now I'd like to welcome Dr. Laura Waldrop up to the podium. And she's going to be talking to us about the NASA Carruthers Geocorona Observatory, a mission update. And from what I understand, it just recently reached its orbiting altitude. Is that correct?
That's correct.
All right.
So far away, you don't call it altitude.
Wow, amazing. So please welcome Dr. Waldrop.
Thanks very much.
There'll be a 2-minute warning.
Great, thank you very much. All right. Let's see.
Oh, it's up now, okay.
It did it. Okay, great. Thank you so much. It is my absolute pleasure to be here. As was just mentioned, yes, we just reached a major milestone. We launched in September, and we are now on orbit more than 1 million miles away from Earth. And so, yes, altitude is a strange thing, 240 Earth radii away. But this is a NASA mission. We were selected in 2019, selected for implementation in 2020, and it's been quite a sprint to get to this point. And the mission is NASA's first mission that's dedicated to investigating Earth's exosphere. So this is the outermost atmospheric layer, originates around 500 kilometers, composed almost entirely of hydrogen, which originated in the lower atmosphere from the dissociation of either methane or water vapor. So this region is extremely important to understand atmospheric evolution through gravitational escape. But more recently, in the last 20 years or so, we see that it plays an incredibly important role in space weather. And so those are the two focuses of our mission. You can see these are our science objectives here. And so we've broken them down into two categories. We'll be investigating two primary science topics. One is the quiet time exospheric structure. So I mentioned it originates at 500 kilometers, but it's actually huge. and it's very difficult to even know how big it is unless you get extremely far away and look back and take a picture or otherwise sense its outermost edges. Images like that have only been acquired 4 times. There are literally 4 images available, and it looks like the exosphere extends at least halfway to the moon. Some of them show it go all the way to the moon, and so it's very difficult to probe this region. It's truly vast. So the first question about quiet time exospheric structure has to do with how big is it? What shape does it have? So does it have an extended geotail formed by solar radiation pressure? To what extent does thermal evaporation, this is where some of the atoms in this region, it's mostly collisionless, they simply evaporate away. Their radial velocity exceeds the 11 kilometers a second gravitational escape speed. To what extent do these thermal processes, this thermal evaporative process, give rise to dawn-dusk asymmetries that reflect diurnal variations in temperature? These are all questions that we don't know the answer to because we've been historically data-starved. But then as far as storm goes, the mechanism by which the exosphere plays such a big role in space weather is through its ability to dissociate and dissipate magnetospheric energy through charge exchange. So it's, as I mentioned, it's populated almost exclusively of neutral hydrogen atoms. They have a single electron. When they encounter either a proton or an oxygen ion, that electron from the neutral hydrogen jumps over to the ion, instantly neutralizes it. It retains its energy, so it flies off on a ballistic trajectory. If it's energetic enough, you can image them. This is the principle behind magnetospheric ENA imaging. You need to know the hydrogen density in order to invert that energy and infer the underlying ion density. But more importantly, what you're left with is, because you've got a hot neutral, it changes the exospheric kinetic energy distribution, and therefore it changes potentially exospheric shape. And what we really want to understand is, how does the exosphere then evolve through this process in response to storms? This is the dominant mechanism by which the ring current loses its energy following a storm. Hydrogen density absolutely governs the recovery rate, energy, the ring current decay rates, for example. Plasmasphere refilling speeds are strongly sensitive to the exospheric density. And so the science objectives here are really straightforward. What are the spatial and temporal scales on which it varies? Again, very much fundamental and yet remaining unaddressed questions to date. Now, we're named after Dr. George Carruthers. As I said, this is a huge region. You cannot just simply send direct sensing mass spectrometers up there. You have to use remote sensing. And he invented the first camera that was able to image its brightest emission in the ultraviolet. So this is an ultraviolet camera. It was initially deployed by Apollo 16 astronauts. It is still there on the moon. Those of you that have gone to the Air and Space Museum probably saw the ground sensor. But this is a picture of Dr. Carruthers holding the film canister. And when we found out that Dr. Carruthers was in fact a 3-time alum of the University of Illinois, and this is University of Illinois' first NASA mission, we thought the serendipity is too good to be true, and NASA embarked upon a mission renaming before launch, which is also rather rare. But luckily, it was very successful. Now, we're going to the ideal vantage in space. If a UV imager, a wide field imager, is the ideal instrument, the ideal vantage is to get far enough away that you can actually see the entire exosphere in one frame. And the perfect place for that is the L1 Lagrange point. This is a gravitational equilibrium point between Earth and the sun. As I mentioned, 1 million miles away, 1.5 e to the 6 kilometers. And you can see we're going to be orbiting a really large 6-month periodicity halo orbit around this point, and then we're able just to simply turn around and stare at Earth relatively continuously. We retain the ability to slew off nadir to target calibration stars, for example, or background scene for photon removal, the background scene. But for the most part, we stay and we simply stare at Earth. Now you'll see there's 2 cones coming out of the little spot called Carruthers. We have a wide field imager and a narrow field imager. I'll talk more about those. But the idea is that we want to sense the entire exosphere in one image, but then we also want to be able to zoom in and see what's happening very close to the exobase and near the limb. So here's the spacecraft itself. It's very simple, very low risk, in the sense that because we're staring at Earth all the time, we can stick the solar panels on the back in a fixed array, and they get sun all the time, right? Power, continuous power. We're power positive throughout the entire operation sequence. The bus was built by BAE Systems. It's not that big. It's about the size of a dishwasher. We launched via rideshare with the IMAP mission back in September, so we were a secondary payload on that rocket in one of these standard ESPA rings, standardized deployment systems on that rocket. The primary science payload, as I mentioned, is an ultraviolet imager. We're targeting the brightest hydrogen emission line. It's Lyman alpha, created through resonance scattering of solar photons. And that was built by UC Berkeley Space Science Lab. Thomas Immel here is also a project scientist, and we've been working extremely closely with them over these last several years and fully intend to. They're also running the missions operations through their missions operations center there. We do have a secondary science payload. You can see it kind of sitting on top. I'm not going to bother with the pointer. When it rotates back around, you see this little thing with these little tripod feet, and it's peeking over the solar panels. That's a student-built secondary science payload. We've got little photodiodes that look back at the sun and measure the incident solar flux that excites the emission, while the GCI measures that backscattered emission off of Earth. So we get the source and the effect, so to speak, of that scattering process. So a little bit more about our instrument. Mentions two co-aligned imagers. We call those channels. There's a wide field imager. It's got an 18-degree field of view. Our vantage changes in radial distance, but that more or less maps to roughly 45 Earth radii away from Earth nadir. It's relatively low spatial resolution because we expect to have really large spatial gradients that far from Earth. And similarly, it's got a relatively low temporal resolution. We don't expect things that far away to change quickly. After all, these are neutral atoms on dynamic orbital trajectories. They do not respond to Lorentz forces. And so they have very long lifetimes. And then the narrow field imager, 3.6-degree field of view, roughly maps to about 7.5 Earth radii from nadir. Double the spatial resolution and double the temporal resolution. And we've been acquiring these images since we first turned on back in October. Now, both of these channels, you can see their optical paths folded in to the actual payload deck here. Both of them pass through identical filter wheels. And so we have a narrowband Lyman alpha. We have two, in fact, narrowband Lyman alpha filters where we're selecting for that Lyman alpha emission. We're trying to suppress all the other emission. Of course, Earth is very bright in the ultraviolet in general. 1304 is very close to this hydrogen. This is oxygen 1304. Very close to the hydrogen 1216 line. And so what we also have in our filter wheel is some long pass transmission bands where we suppress Lyman alpha altogether, and then these are crystal blockers, calcium and strontium fluoride, and then they let in this longer wavelength out-of-band emission. And so we take a sequence, essentially, of filtered images. 90% of our time is spent using the Lyman alpha narrowband filter, and then the out-of-band filters, we consider those calibration operations, but we are getting out-of-band information on a daily basis from Earth. Then once I mentioned the technology, right? You can't just take a picture in the ultraviolet. This was George Carruthers' contribution to our field, the field of remote sensing, converting an ultraviolet photon into a visible photon that can then be sensed with a CMOS detector. That's this UV intensified system here. Essentially, it passes through a cathode, creates a photoelectron. This is Einstein's photoelectric effect. It gets gain amplified through a microchannel plate, passes through a phosphor screen, which then converts them to green light, green colored visible photons. And so all of that is kind of stacked up at the back at the end of this optical path. Those systems are identical for the two cameras. The difference is that the wide field imager with its larger field of view has more mirror bounces to fold up the optical path to fit in there. Okay, these were the first light images. Some of you may have seen NASA made a big splash press release. We first turned on in October, mid-October. We took our first images of Earth nadir in November. And what you're looking at here are these out-of-band. This is an out-of-band filtered image. So the only thing you should really see is either ultraviolet emission from the Earth's disk and limb. So we're talking about in-two bands, especially that oxygen 1304 would be especially bright here. And then the moon snuck into the field of view for this image. That's the circle at the bottom. But you can see, essentially, this is how the plate scale, essentially. This is Earth as projected onto our field of view in both the wide field imager on the left and the narrow field imager on the right. And when you look at this same scene in Lyman alpha, this is where you expect to see the atmospheric glow from hydrogen, not just from oxygen and nitrogen. And it looks like this, very bright. It is huge. In fact, from what we can tell, we haven't seen, we're still investigating, it fall off the edges even of the WFI imager. And so this is still a work in progress, so to speak. This was our first image. But the other thing we've done, during this cruise phase out to L1, it took 4 months between launch and actually getting on orbit in that halo orbit around the L1 Lagrange point. During that time, we did a lot of engineering calibration operations, making sure our pointing worked and our slewing and we were able to stare and so forth. And the very first time we stared at Earth for a long sequence, this was a one-off image. But the very first time we sat and we parked at nadir staring mode, we were exercising nadir staring mode for 12 hours, was January 19th, 2026. And there was a gigantic geomagnetic storm on January 19th, 2026. And we were really excited. We considered that one more aspect of serendipity to this mission. And so these movies are not going to play themselves, but I'm going to show you what is essentially calibrated data. I've hidden the color bar here, but this is in radians, units of photons per centimeter squared per second. I'll have more to say about our unit in just a second. Some of you know this is Rayleighs if you put a 10 to the 6 on it. And this is what we saw. Now, I want to point one thing out here. This was the very first time we pointed on nadir, and there's a little offset. So that's why the image doesn't look round, is because we've recentered it, but that meant we clipped a little bit off. That's now corrected. So don't worry too much about that. But here's what we saw when we stared at Earth on the 19th. I hope I can play the movie. Can anybody help me play the movie? I tested all the movies except this one. Oh no. Oh no. Can I skip it to his frame at the end? Okay, can I ask for 2 minutes to come back up, maybe after the break, and show these movies, because this is incredible. What you're gonna see is amazing aurora. So the idea is that, nothing happens, it looks nice and steady, quiet time, because the interval we caught, it's only the last 3 frames. I wonder if I log out, of the presenter mode. Would that work? But the aurora themselves are incredibly pronounced. And so as it turns out, we're an amazing aurora detector. And for those of you that are investigating, I know this is CEDAR and not GEM, but geomagnetic conjugacy, we see both auroral ovals in the same image, and we watch them change on 30-minute cadence throughout geomagnetic storms. Okay. So it is the first time we've ever shown these movies. I was really hoping to show these for you guys. So anyway, you can see the auroral oval. It's extraordinary. But otherwise, the exosphere in the radiance image doesn't look like it's doing much. But the change in radiance is where the fireworks happen. And that's the one I really wanted to show. What you see is that as soon as the aurora appear, the exosphere, and again, this is a change in radiance. The figure on the left here is mostly white because there's no difference. Nothing's happening. When I say change in radiance, it's relative to the pre-storm quiet baseline radiance image, and then we watch changes in radiance happen. Right now, it's all white. When the aurora when the aurora happen, the exosphere slowly gets brighter and brighter in a wave that moves out from the Earth. So come find me. I have all the movies on my own laptop. We'll show them there. But we're really excited about what that means. So the implications are, number one, anybody using a density model, these have historically been spherically symmetric and time invariant, you're gonna get the output wrong because the exosphere is incredibly dynamic. We suspected it, built a mission around it, and this is the first time we've shown that to be true. But the other is that there's some really exciting physics happening. What you're gonna see is that there's a 20% change in radiance over 30 minutes. And this is something like a 40% change in density at 1 RE altitude. So this is big news, and you'll expect to hear a lot more from us and our team on that. So as far as, now it's not advancing. Let's see. Here we go. Carruthers data products, what you can expect us to be releasing. Obviously, from the spacecraft, we get level 0 data. This is just the raw images and digital numbers. The first thing we do is kind of clean them up and sort them to make it easy for users to find what they're looking for. We resolve the timestamps. We remove voltage bias, which is a bunch of vertical stripes in the image imposed at readout, camera readout. And then we start on the calibration. So the first step, level 1B, we consider with all instrument effects removed. So the dark current, we flat fielded them. They've been geolocated and registered and centered and oriented so that north is always up, that kind of a thing. And then we subtract photon backgrounds and calibrate them using stellar calibration into physical radiance units. This is definitive now. We will be releasing that data as 10 to the 6 photons per centimeter squared per second, not per steradian. We've had hours of discussion about this. We consider this the true unit of Rayleigh and not the other imposter. And I'm happy to discuss that with you as well after the meeting as to justify that choice. And then we use those images to derive hydrogen density. We'll be releasing 3 different types of products for that. One is there's 2 what we call level 2A products. One is that we take the image, the NFI images, we use radiative transfer model inversion to model the optically thick, multiple scattering environment near the dense lower atmosphere right off the limb, and we derive thermal density at the exobase. Once then you get farther away from the planet, it is now potentially highly non-thermal due to the chart exchange interactions with the plasmasphere and ring current, and at that point, but then it's optically thin. So we can retrieve total density in the outer exosphere. When we have a quiet time baseline, we use tomography similar to the MRI scans. This is a technique that was developed for twins data originally. So we can get 3D reconstructions, and then we put it all together and get a full global map. So as far as milestones, I mentioned we launched, we had instrument commissioning. The only exciting thing, I bet this one's not gonna play either. Oh, well, I guess it does. The only really exciting moving part that happened during instrument commissioning was the doors popping open for our apertures. Obviously, we wouldn't have a mission if that hadn't gone off without a hitch. But we'll be delivering our first data to SPDF no later than September 1st. We're targeting mid-August. And then we've got a nominal 2-year science mission. Our special issue for Space Science Reviews should be coming out soon. We'll upload the papers on archive in advance of data release. And then we've got a special session at AGU. Please submit abstracts if you're interested in that. And more than that, please reach out to get involved. There are a ton of science opportunities for collaboration, both with ground-based observations, with modeling, and we just couldn't be more excited to be here and to have reached this point. I think many, many more exciting things to come. Thanks so much.
Thank you so much, Laura, for that wonderful talk in this very exciting program. And we would like to offer to have you come back up right before the coffee break, so you can show your presentation.
I'll bring my laptop.
Bring your laptop, and you can talk to the AV people over there, and they should be able to provide you better support.
Fantastic, thanks.
Thank you so much. And next, I'd like to welcome Jens to introduce our distinguished lecture speaker. Thank you.
Good morning. I'm Jens Oberheider from Clemson University, and it is my great pleasure to introduce our 2026 CEDAR Distinguished Lecturer awardee, Dr. Larry Paxton from Johns Hopkins University Applied Physics Lab. So Larry receives this award for his pioneering experimental work on ultraviolet remote sensing of the ionosphere and thermosphere from space. Larry's work has fundamentally shaped our understanding of the upper atmosphere and helped to define modern CEDAR science. Larry has served as principal investigator for 7 spaceflight instruments, and most of us heavily use these data because he was a PI, for example, of GUVI and SUSI. Data from these missions transformed our understanding of thermospheric composition, geomagnetic storm effects, auroral energy input, and equatorial plasma bubbles. Many of the discoveries we now take for granted in aeronomy were made possible because Larry built the instruments, developed the algorithms, and championed the observations needed to test theory against reality. Beyond his scientific contributions, Larry has been a tireless leader and advocate for the community. Larry has served in numerous national and international leadership roles, including president of the AGU Space Physics and Aeronomy section. And I cannot really recall being at any AGU or CEDAR meeting over the past 15 years or so without Larry being there and sharing his excitement about being an experimental aeronomer and advocating for new space missions, including GDC and dynamic. And just as importantly, Larry has mentored generations of scientists and engineers with truly remarkable enthusiasm and generosity, including myself when we first met about 15 years ago. Larry's impact is reflected not only in his more than 300 publications and way over 10,000 citations, but also in the vitality and direction of our field today. So please join me in congratulating and welcoming Dr. Larry Paxton, and I'm sure we will see a very entertaining, distinguished lecture.
So
You get to choose either that one or that one.
click on the red one. Oh, so there's a timer. Good.
Yes. It'll blink
It'll
yellow
start.
when it's 2 minutes.
All right.
Okay.
Great. Well, thank you. I didn't really recognize myself from the kind words from Jens. So, and you know, people always, I've seen many of these distinguished lectures, and you know, they always say how grateful they are. And I always said, yeah, well, but I think I really am, and I really appreciate it. So thank you very much. So I'm going to try to provide some value to you. So let's start. As Jens said, my selection letter had two things in it: the science part and the, you know, my wacky ideas and mentorship and whatever that is. So what I thought about is, how do I do that in justice in really just one talk? So I'd like to offer you the choice. I prepared fully 2 one-hour talks. Okay? I'm not kidding. I'm not going to give both of them. I am prepared to give either of them. Okay? So there is the blue pill, like in the Matrix. Yes, go back to sleep and just keep doing what you're doing and hope for the best. There's a red pill, which is to take a look around and see, what do you want to change in your life? How do you want to change the future of your life and the lives of your friends and colleagues and move ahead? So what I want you to do is, let's have a vote right now. Red pill. How many people want red pill? Okay. How many people want blue pill? Okay, I will give you the lecture personally for 1 hour, okay? And my consulting rate is $500 an hour. I just defined it right now as 500, so you're good. So thanks. We have a handshake virtually on that contract. Okay, good. That's a joke. By the way, if I make a joke, I'll try to raise my hand so you know that I'm not, well, completely serious. Okay. So here's the disclaimer. By the way, when I talk about red pill and blue pill, there's so much stuff going on around us in the world that's rewriting all the social norms and stuff. I just mean no crazy stuff, no unusual, no different stuff. I just mean red pill being aware of the truth about reality, and it can be upsetting to reorganize your thinking. It is not a political statement or anything else. Taking the blue pill is choosing to continue along your current path. I feel awkward even having to say that. So the topic for the red pill talk, which should show up as red on the screen, is everything is transforming CEDAR in your career. So that means I'm going to talk a lot about the building blocks of how to think about this. I'm not going to tell you the solution. You have to do the hard work yourself. You have to build it in yourself. But I believe in you all. You have these resources inside yourself, or you wouldn't be here today, right? So it's some thoughts on my own career. I'll tell just a little bit. And it's really life as a human and the realities of the world, because we have the problem of communicating our internal values to the rest of the world. All right, so I have a whole bunch of stuff in here. I'm not going to really talk about it, but Jens has already given a very kind overview of my experience. But what happens is when you start making up all the list of things you do, so I've done a whole bunch of stuff with instrumentation of different kinds. I've done instrumentation as PI lead for both NASA and or DMSP and other things, chief scientist for large mission. It was over a couple $2 billion, worked on many, many spacecraft, sounding rockets, shuttle flights. My current interests are in VLEO and hypersonics. Variety is the best teacher. I've done a bunch of things with patents and provisional or invention disclosures, about 16 of those and 1 patent. Spin-off awards for transition to technology and things. The NASA Institute for Advanced Concept, 2 PI awards there. 1 for AI-enabled robotic exploration, another for data from GEOs, satellites. But I think really the thing that Jens talked about very, very briefly was, of course, and I won't go into all this, is other people are the best teacher. You learn from perspectives that they have. And I was elected a member of the International Academy of Astronautics, and the International Astronautical Federation recognized me with the Distinguished Service Award. I've done a whole bunch of stuff for small satellites, knowledge management, integrated applications. So these things that I'm sharing with you are lessons that I've learned from other people. And of course, oddly enough, I actually served on the CSSP, and we worked together in the early 2010s on a vision for CEDAR. And I'm a member of a technical committee for the IAA and stuff, and organized many sessions at various things. I have a session, in fact, on the fall AGU about the VLEO environment. I hope to see you there. So I'm going to be telling you stories right now about things that I find relevant, and I think, to me, the easiest way to internalize these lessons is through stories. And so I hope they're relevant to you, they're relevant to me, but I believe that as a community, we have to change the way we think about things. We have to make sure that we convey value, and just the fact that it's interesting is not sufficient. Success is not guaranteed in any of this, and accepting that is hard. After all, you've spent your whole life doing this stuff, however old you are. And it's hard to talk to somebody and they just look at you blankly with this idea like, why in the world would I care? If that's their reaction, it's on you, not on them. And we can practice that. But the thing to bear in mind whenever you're faced with success or with failure is there are always exogenous factors that affect what happens to you. You don't have control over those. What you have control over is how you react to that. For thousands of years, people have been dealing with these things. Take lessons from that and find peace in yourself and the bravery to continue. Overcome doubt, fear, accepting risk, living with uncertainty. Those are heroic and stoic virtues. You're not alone. Thousands of people have done this before for thousands of years. They've lived in turbulent times, far more turbulent than we're living in right now. It's upsetting to us because we're exiting a golden age of science when the value of science was not questioned. For the students that are working on a thesis, my advice to you is to remember, you are not defined by your thesis. Don't let it define you. Let it be the foundation for what you do in your life. Maybe you want to do this for the next 40 years. But remember, you can grow from that position. And every one of you has achieved extraordinary things. If there's anybody in here that wasn't consistently in the top of their class, please raise your hand. We won't laugh. No, I'm serious, but, oh, sure, I forgot to raise my hand. Okay, no, but the thing is, everybody always achieves, and we're used to a high norm, but that's very unusual in the world. Now, there's a great little book called Who Moved My Cheese, and it's sort of a fairy tale, fable kind of thing, but it's very popular in management circles. Now, we think about publications, JGR, Science, Nature, whatever, but there are literally thousands of journals on management and thousands of books on management techniques, on challenges of management and things, and they are very popular. But Who Moved My Cheese talks about a simple parable. There are little mice running around in a maze, and there's always cheese at the end of the maze. And so they get used to the cheese. That's money for you that aren't, thinking parable-wise. Okay, so it's always in the same place. One day, guess what? The cheese isn't there. So some of the mice are like, well, who moved my cheese? I should wait. The cheese will reappear in the same place in the same form. A couple of the mice are like, hey, maybe what we should do is look for new cheese. Well, but is that going to be cheese I like? Is that the cheese I'm used to? Who knows if there's cheese way over there? Let's wait for the cheese to show up again, and maybe there will be a little. Sometimes it's very easy to do that, to think that things are going to get better. There are no guarantees in life. So there's another book that I like quite a bit, and it's about the hero's journey, Joseph Campbell, The Hero with 1,000 Faces. Again, going back to this idea that people have dealt with these problems for thousands of years, and myths always show a common structure. In fact, movies show this too. Think of Star Wars, for example. There's always an inciting incident. There's a crisis, transformation, and a new life. So today, we're all faced with this hero's journey. Can we transform our life? The hero is, in the myths, is always pulled back from the usual world, pulled forward from the usual world into the unknown, faces a series of trials, meets those new challenges, and if they are successful, heroes are not always successful, you make a transformation. The hero takes a place in the world, it brings back to the world knowledge, benefit to the world. There's this quote from one of my favorite books, David Copperfield, not the magician guy, it's a joke, but by Charles Dickens. Whether I shall turn out to be the hero of my own life or whether that station will be held by anyone else, these pages must show. Think about your life that way. Are you the hero of your own life? That doesn't mean you're better than anybody else, but that you took heroic steps to create your own life, to do the hard things. These stories that we talk about, they convey these universal truths, that it is hard. Now, science is hard. Discovery is not iteration. Science is a contact sport. Ideally, you learn by being bruised and battered and questioned. But trust in your skills, believe in yourself, and you can flourish. And I believe that everybody here has completed the hero's journey just to show up at CEDAR, because it's very, very difficult. You've probably seen many of your fellow students that fall away. They do something else or they take a safe job. They don't dare to be different. One of the key ideas in Joseph Campbell's books is follow your bliss. If you follow your bliss, your inner happiness, you put yourself on the kind of track that's been there all the while waiting for you. You haven't realized it, maybe. Follow your bliss, don't be afraid, and doors will open for you that you didn't even know about. They're gonna be there. Paraphrasing that. So the first step in the hero's journey, of course, is leave the ordinary world. Our ordinary world is focused on small problems. We think about small problems because we have small grants that are getting smaller every year. They're driven by smaller budgets, which are driven by politics. The politics arises from the lack of a value statement. There's plenty of money out there. And this is why we have to establish a value statement. Why is what we do important? And it can't be a message that, we say to each other, this is why it's important. Oh yeah, I agree, no. So, I'm gonna tell you a story. One time I'm in San Francisco, I'm walking along, and you see all kinds of crazy stuff at the AGU in San Francisco, and there's this tech bro sort of kneeling on the ground at night looking for something, and a cop comes up and he says, "Hey, what are you doing?" He says, "Well, I lost my keys, down that dark alley there." And it was conveniently marked with a sign that says dark alley. So again, and so what happens is, well, why are you looking here? Because that's where the light is. And that's what our science is. We're surrounded by darkness with one light source, whatever instrument it is or whatever else we use. And what we need to do is change from what we call the scarcity mindset, that I can only operate where there's the light that I know, or where I found cheese before, to an abundance mindset. Now, this is not magical thinking, by the way. The abundance mindset is the belief that there are always resources and opportunities if you open your acceptance criteria. The scarcity mindset is the belief that life is a zero-sum game. And this is another management book. Scarcity mindset, core belief, life is a zero-sum game. The central question is what is missing, lost, or unavailable. Sartre would say that this is the nature of human beings, to feel the lost, not the positives. You view others with fear, envy, suspicion, and the belief that to succeed, others must fail, like in a competition for grants. The time horizon is always short. How do I survive to the next time my grant kicks in, or I can work to make sure that other people don't have access to my data or whatever, all kinds of things. The abundance mindset, though, the core belief is life is abundant in its possibilities. And what I want you to think about is, of course, that you have this skill set that is very rare. You can apply it to all kinds of problems. When the opportunity space, which is defined by things that you can't control, changes its focus. Don't despair. Don't look for cheese in the same place. Think, where else can I look? Did I, by accidentally meeting somebody and became my thesis advisor and starting a thesis and doing research in this, is that the most defining lucky thing in my entire life? Does that define me? Or can I choose a different adventure? The central question is what's available, possible, and might be created. Now, I'll mention this later on, but see, I'm forced to think that way all the time because APL, the Applied Physics Lab, is a coin-operated machine. I got to have coin continually to do any of the things that I like to do. Because of that, this is the great thing about the environment I'm in right now, is I have to work with others, and I have to recognize the equality of others and the value of others, and make sure that collaboration works so that everybody succeeds. And success, of course, comes in many forms and many timescales. I'm looking for long-term growth, and I invest in others to create opportunities. So the abundance mindset is, hey, there are more than one streetlight out there to look for my keys, right? If I take the transformative abundance mindset and I practice gratitude, and I try to do this every day, think about the things that are good in your life. Don't think about the things that are missing. You find that the landscape is lit up in many, many different ways, in ways that you didn't even recognize. So just think about that story, that little story I told you. The person that's lost their keys has many options of looking for them, right? They don't have to try to find it right under the street light. They can, you could call a rideshare. You got a phone. You could even use your phone. You could ask for help. You find another source of illumination. You wait until a new dawn. It all depends. How many of those can you think of? Think about this in your own situation. And that's what I want you to do, is think about transforming your life over the course of your career and looking for that bliss. And I've talked about this before. One of the things that you see is that people say, well, I'm not really happy right now. I envision, I'll get better. But what I want you to do is think, if I was looking back today, and I'm looking back on my career, and I'm about to end my career, I'm looking back, what would make that worthwhile? What would be the things I would like to see along that journey? And how do I get to that end state that I'm going to find satisfying? What things do I have to make happen in my life for that to come true? And every year, try to move along. Now, what will happen is those goals will change, but you have to be able to adjust and accept that my goals have changed as I learn more, as my life changes, as I go through different life stages, and my priorities change. But always have in mind that you're trying to go somewhere with that. The scarcity we're experiencing in science and technology in the United States is turbulence. Turbulence is, of course, small scale. So what we see is small scale things. We're very sensitive. The whole geospace program at NSF is about 1% of the CEDAR budget. 1% of the NSF budget. And there are big things that are happening, but it's because we're looking at the smaller scale, and it is a tragedy. It's a personal tragedy. You don't want to undermine that at all. There are terrible things happening, and our ecosystem is being disrupted on those scales, but we can take steps individually and collectively to manage to live through that. You own your own life. I want to go back to this idea of why did I say we're in a golden time? It's because 75 years ago, Vannevar Bush published this report called Science, the Endless Frontier, and it created NSF. In 1950, Congress put that in. It defined basic research as practical innovation and curiosity-driven, and it codified the things that this was to do: national security, health, and prosperity. Curiosity-driven science was intended to address those three core values. Now, I'll just say very briefly, as a student, there's what I call the bamboo model of academic research. What happens is that in this response to World War II and GI Bill and all kinds of other things, there was an environment in which there was an explosive growth of colleges and universities, and we were encouraged to grow in a linear fashion as fast as possible. And the way you propagated yourself, you cloned yourself by your graduate students, postdocs, and they contended for resource against others like you, but there was plenty of money to go around. I'm going to suggest that we benefit from that fundamental change in society because, of course, they realized that there was a need for developing talent, the National Defense Education Act of 1958. Now think, how many programs today do you hear that are as visionary as this need for investment in the infrastructure? Hundreds of millions of dollars was devoted to writing text and creating STEM programs, and it transformed universities. There were very few what we would call R1 institutions back then. And so it was, again, funded heavily by the United States government to win a geopolitical technology race. And we can talk about why Sputnik was such a shock, but I don't want to take too much time. But so this was all to support economic growth, new industries, and employment. And they were recognized as the values of science investment. So think about what we hear today that sometimes is upsetting and map that back to what was the foundation of the last 75 years of the science enterprise. Now, when we talk about things, there's this thing that I talk about often is Maslow's theory of human motivation. And there are various stages. There are properties that must be satisfied. Now, nations, we can see it in history and in the Common Era. They stand on economic benefits: food, water, physical security via soft power, which is like creating a wonder, going to the moon, landing a probe on Titan, establishing AI data centers in space. But ITM science, or CEDAR science, connects to more than just this highest goal of self-actualization. This is what we have to do to experience our fullest lives. Now, what I want to say is that first is, there has to be the basic needs, human needs. And as you go up, there's self-esteem, but self-actualization, that sense of wonder, that's what we get to experience all the time. That is curiosity-driven research, and that is something that very few people ever experience in their life on a day-to-day basis. So we're very fortunate. Now, I don't think the cheese is really moved. We can think about the same cheese in a new wrapper by looking at these things like safety and security and physiological needs. So there are things like, the safety in your person, that's the security, national security. There's food and water security. There's the economic benefits. And we tie back to those. So I won't go into this very much, but I want you to think about life as an oak tree rather than bamboo. As a student, as a seedling oak, you try to grow straight up. You try to build a great root system, a foundation for your future life. But then as you grow up, you start to branch out to build a healthy system. And you're part of an ecosystem that is different. It's not the same people doing similar things. They're varied people that are, live under you, protected by you. There are other kinds of animals and trees that are part of that vaster system of interlocking abilities, responsibilities, and capabilities. So, change is hard. You've acquired the skills to grow, though. And I'm going to tell you a little bit about that. So remember, I keep saying I have faith in you. Well, you're all smart. You've learned the basics, the hard stuff. And so the Pareto distribution curve, which you see here, this is sort of like learning stuff, progress, evolution. It's the logistics curve. It's a universal curve. It's found in economic systems and ecological systems, but it's also found in your education. Time goes on, and you start out in school, and you go to high school, college, graduate school, and it's really hard. You're learning all this stuff, and of course, it's tempting to say, I'm never going to use all this stuff again. But you're building this foundation, and finally, maybe if for the students out there, you've noticed that all of a sudden it starts to make sense, and it's making more and more sense, and you're gaining more and more capabilities. But as you go along, notice what that curve does. It says time goes and increases, and your progress starts to slow down because you're refining to the exquisite degree knowledge in a particular area. But the reason why you have the capability of changing because of what Pareto called, what is commonly used in commerce business, is the 80-20 rule. That once you get to about the 10% level of capability, you're in that rapid progress region where you gain in 80% of that additional capability in 20% of the time. So that 20% of the time, that's your time as a grad student and postdoc. You're building capabilities that allow you to go in different directions. You can continue to grow straight and be on that hard part of the curve, where you start to do more and more difficult things that are refining ideas and capabilities, or you can change your modality. So that's the thing, is to learn applications and extensions of your existing skill set. So, of course, I've written a couple of chapters on this kind of stuff. This is the kind of thing that you typically see in companies. Some of the great companies like Xerox, IBM, Kodak, Nokia, there are many of these companies that have started out, they had this growth curve, or doing great things, and they succumbed to various challenges. And one of them was, at the top there, is arrogance, where they think nobody can beat us. They fall off in relevance, they decline. As the curve goes forward in time, you start to decline, and you'll see all kinds of pathological behaviors on the part of companies and management, because what's happening is they try to get back to where they were. And it's a human thing. Things were good. I want to go back to when they were good. But the world has moved on. You can't recover that. So, again, take away this idea. These lessons apply to science, basic research, as well as commerce. Now, the hero's journey we're talking about, things that, what I'm trying to give you is ideas about how to manage your future. There's 5 laws that everybody ought to know. There's the Dunning-Kruger effect, which is dumb people like to dumb, and smart people don't realize how smart they are, how knowledgeable they are. That's the second part of Dunning-Kruger that people forget. There's the Pareto principle I just covered, the 80-20 rule. There's Parkinson's law, which is tasks always fill the available time, and I'm going to speak very briefly about that because I only have a brief amount of time. So that was sort of a joke, but okay, so Hanlon's razor, please don't attribute malice to what people say. Look beneath that, assume the best. And the Peter principle, when you're dealing with management, that they all tend to rise to their level of incompetence in management. So I'm going to talk a little bit about management in just a second. Now, I'm not going to go through all these, but when we're talking about change, the first thing we have to realize is that we have to deal with management in your company, in your university, in the organization you work in, whatever subunit it is, and they have different motivations than you do. There's a vast amount of literature on this. I won't go through all of these, but one of the things you have to do is understand how to present your idea in a way that they can connect with. And there are all kinds of things that are obstacles to that. I wrote a paper on knowledge management transfer, and how difficult that is, that nobody wants to read, but that's okay. Anyway, so change is hard. Now, what you need to do when you're going on this journey is you need to express why things have to change. You need to define success measures. You need to get leadership support. That was that previous slide. You need to understand that they are not good with risk. And you have to demonstrate early wins. And you want people involved in the process. And that's part of what I'm telling you about is get involved in this because we have to change. So let's think about it. The Heidelberg Catechism, DARPA, does great things. It dares to do incredible stuff. So the first thing in the Heidelberg Catechism is, what are you trying to do? Articulate your objectives using absolutely no jargon. More words don't help. Lots of times I find that if people are trying to explain something to me, they just add more words. Big question is, why are you doing it? So there are all kinds of other questions you ask. One of them is, if you're trying to do something new, you're trying to sell an idea that you have developed. First thing is, how is it done today? And why is this better? There are lots of other questions that you have to look at, but I would say, take a look at the DARPA site. It can give you some ideas. And the reason I'm bringing this up is because we're gonna have to look outside of just NASA and NSF support if we're gonna prosper. But there's a lot of money sloshing around in the system in new ways. So, how do you improve your life and the life of others around you? Learn patience. Some can learn, some can't, and some will not. Cultivate beginner's mind. I'll talk about this in just a second. Share the excitement of what you do. Be open and enthusiastic about new experiences, not afraid. That's really hard. Don't focus on the details when you're talking about your expertise. Make your story about their story. And if you find it hard to explain what you do, have you ever tried explaining to your relatives or family members, why are you working on? Why is this important? Who cares? Lots of times their friends will say, oh, okay, good. Yeah. But they're not excited about it. They don't share your interior excitement. So what you need to do is practice developing a story about why what you do matters. And that means don't talk about the details. Talk about your contribution to the bigger picture. And that helps people understand why you're going where you're going, why you're investing in this, and practice your story. The people at APL, they know I'm very annoying. I will practice my story for a pitch. I don't say, hey, I'm going to give a pitch. It's like I walk down the hall and I see somebody. They say, how you doing? I say, well, I'm working on, and then I give them the pitch, right? And if you can't do it in a couple of sentences, then you need to adjust your pitch. And if they say, well, that's been done before, that's valuable information. Redo your pitch. And so build more than one story. You can do the same thing, but you can look at it from different perspectives and understand that. And so have different perspectives ready and try them out. See what works for different audiences. So remember those 5 laws? So I want to just hit one other thing I see scientists do all the time. Parkinson's law, the idea that time fills, tasks fill the available time. Academic writing is something that is an unfortunate mindset. As a community, we feel that we have to write to produce a compelling narrative. We write actually for each other. But what we really need to also do is to understand how we communicate to other people, because written scientific communications really presume interest in the knowledge, interest in the reader, knowledge, and a commitment to read your paper. But that's not the way the real world works. written scientific communications are not the way you establish value and the way that you establish opportunities for your organization or your community. In fact, I could talk a lot about how to write a CV. I won't do that right now, of course. But if you want to establish new opportunities, it's not by how many science papers you've written on a topic. So just as an example, posters, So you produce a poster, like on something like far UV imaging of auroral dynamics. Oh, everybody ought to be interested in that, right? Well, the problem is, just as the parable of the poisoned arrow, lots of times you're focused on all the details. In the parable of the poisoned arrow, somebody's wounded by an arrow, and they want to know what kind of arrow was it? Was who made the arrow? Who was it? What class was the person from that shot me with the arrow? And you're dying of poison, and you're waiting. No, I don't want to see the doctor yet. I want to know all these questions. And so what happens, though, I think, maybe it's just me, when I see a poster, I don't want to get too close because I'm afraid I'll get sucked in, and then, I'll be, I don't know what the poster's about. They want to tell me all these details, and I want to know some basic questions. And there's a book here, about how to do this, how to communicate. So what I want to know is, just looking at it, without getting too close, is this something I'm interested in? And maybe if I don't know you, that's more of a concern, right? But if you don't know your audience, you want to somehow get people in so that they will want to hear more about your talk. And what it is like they want to know, hey, why do I care about this? And, the poster process, basically, you have a captive audience. What was it, 52 judges? 62. You got a lot of judges, so it's going to look like there are all kinds of people that are interested in you. I just caution you to think, how would I tell somebody who doesn't know or is not obligated to look at my poster? How do I communicate that? For me, I'm looking at always, what will I be able to do that I can't do right now? What's new and exciting? That's the key thing. And what's in it for me? I'm a very selfish person. I want to know what's in it for me. How can I spin this into something? So transform that hazard of the black hole into a feature. Attract people in and get them engaged with you. Because if you're trying to build your career and make connections, a poster or talk is a good way to do that. But you have to get them there. Now, I'm only going to go on. So this is intended for you to have as a reference if this is an interesting talk. There's all kinds of things here. I want to talk just briefly about maladaptive behaviors. One of them is always starting at the very last minute, endlessly tweaking things, never letting things go. Who works until the very last possible minute before submitting a proposal? Anybody? I do. I always work to the last minute. I always think that if just get a little bit better, explain this just a little bit better, but I don't revisit the whole idea, like, what am I doing and why? So these things arise from normal human emotions, and one of the most deadly is inability to escape perfectionism. So, remember Parkinson's law, try to be aware of it. There are scientific journals that study all this kind of stuff. Here's an example of a model of how that avoidance procrastination leads to a forced choice, which is always bad. So I think, we tend to believe that details matter, but rarely do they ever matter to very many people. Certainly not in terms of starting new programs or crafting a compelling global scale initiative. We value correctness. That means we always want to get things exactly right. That's hard for us to let go. Always start with why, then what, then how. That engages more people. And of course, remember I've already talked about this, how no message is universal. Engage people with it. There's a great book, Start With Why by Simon Sinek. Talks about the art of communication. Very good tips in there. Let's think about NASA and NSF a little bit differently. We look at it as one organism that's undergoing contraction. Is the contraction really occurring? No. Even though there have been big budget cuts, we've had advocacy coalitions that have pushed back on those. The value of the organizations is recognized by Congress, but what we see again is turbulence. We see at our small scale the big changes that affect us. But there is a shift towards partnerships with industry, government labs, international organizations that creates more ways to create and execute opportunities. University environments are much more agile than some of the larger labs. Now, again, I want to stress this idea. This is part of that abundance mindset. Think about things. It's not predicated on more money for you. It's the idea that there's money out there. You just have to change the way you think about what it is, where it is, and how to get it. And always bear in mind that you do meaningful work. You need to think about what's going to make me happy. What's my goal in life? Where do I want to be? And maybe it's just have a job. That's perfectly good. One thing I do want to hit on very, very quickly is I think the American Geophysical Union must act as a labor union. The reason why, we can see it right now. How many of us feel protected at any level? Labor unions can do enormous things for people. Why now? Of course, employment stability is a big question. Things like workload, staffing and responsibilities, benefit security in your job. So I'd like to leave that as something as an action item for people to think about. Can we change the American Geophysical Union from an affinity group, a club, into really a union that advocates for us? They've sent out more and more of these calls to action. Pay attention to those. So what's one of the enabling things? The challenge, of course, is beginner's mind. I don't know, but that's okay. And this is a Zen statement. In the beginner's mind, there are many possibilities, but in the expert's mind, there are few. Now, it's a razor edge between that attitude and the Dunning-Kruger effect of thinking you know everything and you know nothing. But, think about children. They're eager. They are open and accepting. The expert's mind can be challenged by differences. Try to grow out of that. Learn to be humble and open to new experiences. And remind yourself, I am where I am because I can learn. I can do the hard work of learning. I can eat bitter. I've proven this many, many times. Every one of you has done this journey. I am worthy of the opportunity to learn, grow, succeed, and be happy. So part of that, being a successful PI leader, team member, there are core responsibilities, but I take issue with the way that being a PI, being a leader is presented by NASA. The PI is the sole responsibility, meaning it's their job to make sure the team functions. Sole accountability is different than sole responsibility. That doesn't mean they have to do everything. So one of the things I'm asking, if you want to lead in a particular direction, think about how you form a team. And that means getting people to feel vested so that they understand what's in it for them. Now, PI is accountable for a bunch of different things. Some of them are summarized here, but the core idea to carry away is that the PI makes sure that important decisions are made by the team. That's their goal, not to make the decisions. Make sure that everybody there understands why we're going. And the problem is that sometimes we revert to a different mode of deciding things. So, core idea, if you want to cultivate heroes that are capable of going on the hero's journey, take care of yourself, be a hero yourself, take care of your team, make them feel safe, valued, ensure they see value for them. There are other things, of course, bad PI traits are, you don't trust the team or feeling responsible for details. The more you appeal to your authority, the worse it'll be, the less authority you end up with. Cultivate emotional stability in yourself. We're all going through trials. There's lots of things that are hard to do. Evaluate what's important at all points, like that trip through your life. What's important and what's not? What's a distraction? What are the things that aren't important to your goal, to following your bliss? Share credit with your team. Always share credit. Take care of the team first. And there's a book, a great one, another one by Simon Sinek, Leaders Eat Last. Great leaders always take care of their team first. Think about that. Think about your life. Think about your experience of other people. What kind of leadership role do you play? Well, there are all kinds of different values here. The challenge is there are different leadership styles. There's, this is DISC, D-I-S-C. Again, huge body of literature on disk management. There are different personality types. And you'll see on the y-axis, there's this tendency to, there's a range from acting to assessing or not acting, contemplation. And there's task-oriented versus people-oriented. So there are people that direct and decisive, they tell you what to do, they expect you to do it. There are people that are analytic and cautious. That's how they manage. They tend to want to have, they focus on tasks, they want to have a lot of time. There are people that are inspiring and active, and there are supporters. And of course, where are most scientists? Well, we're down here in this corner most of the time. You want to have lots and lots of time. You want to have full task-oriented, and you've got to be absolutely correct. So, to be an effective leader, you have to adjust your style for the type of people you're working with, because teams aren't all the same. There are people that are scientists, there are people that are engineers, there are people that are administrators, there are people that are support staff. They all have different goals, and they all exist in different quadrants of this chart. So we live in challenging times, right? Nobody ever started a heroic tale or a fairy tale with, once upon a time, nothing much happened, yeah, okay, yeah. That's part of the nature. So we've been told that the cheese has moved, really. Or has it? It's changed. And we heard from Joe Westlake's town hall meeting a couple weeks ago. And again, we heard that there are these themes in heliophysics RNA. Whenever I'm looking at one of these things, I keep thinking, okay, where am I? How do I fit in? How am I going to make some money out of this, But, somehow we took a wrong turn. In 1963, John F. Kennedy gave a speech at Rice University, and it's an inspiring speech. I won't go through it all here. But, the idea was there was this enormous goal. We were going to go to the moon. This is 1963. We only put people in orbit a couple of years before that. Amazing, right? And so he said, this wasn't going to be easy. It wasn't going to make people rich. It's something that will challenge us in a way that we've never been challenged before. And he outlined that there were other goals that we were going to pursue. We were going to do all of these difficult things. And we lived at that time in the land of opportunity. That's how we referred to the United States, as the land of opportunity. Have you ever heard that in the last 20 years? That was the abundance mindset. And we changed to a scarcity mindset. There were visions of what the future was going to look like. The future was different and better. It was not just the new iPhone version that was slightly better. It was going to be transformative. We were going to go to the moon. We were going to go to Mars. And 2 months after that speech, just 2 months, Kennedy was assassinated. But in less than 6 years, we're on the moon. Could we do that now? And why? It's an interesting question. So, trade has driven history and shaped society. Here's a couple of books. But basically, the idea is that, core idea, looking back, we see all these great heroes of exploration. But exploration was rarely ever funded out of scientific curiosity. It required massive capital outlay. The investments were made only when there was a promise of an economic benefit, a new market, a new monopoly, fresh territory for corporate wealth extraction. Well, why do I bring that up? Exploration now is led by the merchant princes. There's Blue Origin. There's Blue Ring is doing something, they're constructing this space station in space for commercial use, laboratories in space, an orbital reef, billions of dollars. SpaceX returned to the moon, and the other things, SpaceX wants to do moon missions, support. There's also talk about lunar mining. But SpaceX even has this thing, we aspire to be a galactic civilization. That's astonishing. And the guy's only a trillionaire. I mean, what could you do? So again, how do we fit in there? The space technology market is increasing every year, and it's starting to go through this exponential trend. And if Elon Musk builds even a fraction of his million satellite AI constellation in space, it will be, again, transformative. What's our role? Now, you know, NASA talks about going back to the moon. And these plans look remarkably similar to the ones from 65 years ago. There are interesting problems to be solved. And Laura mentioned in passing George Carruthers. A couple of us back there in the table, Paul and Joe and I, we knew George. George was a funny guy and a great guy. Scott Bailey also knew George. That's where I met Scott, was at NRL. He was 16 years old. That was about 5 years ago, I think, right, Scott? Anyway, that's a joke, okay. So, but the story is, sometimes we return and we can be ready to think about the science we would do from the moon and about the moon as ITM scientists. So, trade has produced remarkable capabilities. Here's a plot of mission cost, or total mission cost, launch cost. And so if I said, hey, you know, how much would it take to put 750 metric tons in low Earth orbit? Well, if I do Artemis launches, it takes about 8 of those SLS launches, so that's about $18 billion. But that curve shows the price per kilogram declining over time, and with the Starship target right around $200 a kilogram and the total mission cost. So for around $100 million, I could put 750 metric tons in low Earth orbit. Well, why? You know, what is that? Well, first of all, anybody see 2001, the movie? Okay, so the ship Discovery in 2001, in Arthur C. Clarke's book, was 750 metric tons. It was a nuclear vessel that was going to go to Jupiter. 500 tons was required to build, staff, supply, and maintain the Antarctica Bird and South Pole Station during Operation Deep Freeze. So that's the order of magnitude we're talking about. $100 million might be what's required to do something enormous in space. The other point, though, since I'm talking to CEDAR here, is CEDAR, we can redefine success because of this low cost to orbit. And we can use industrial parts. We can no longer attempt building spacecraft where mass-constrained solutions demand sophisticated technology. No more watchmakers in space where everything is just finely done. Slap something together, if it only costs $100 to launch a kilogram, or $200 to launch a kilogram into space, then getting something built, you know, at commercial scales becomes possible under CEDAR. That can be transformative. If you're in a scarcity mindset, you say, well, but then that's, you know, money that doesn't go to, you know, all these other things that we've got. In the abundance mindset, say, hey, I've now got a great story for NSF, that NSF is enabling students, faculty, science in space with space instruments built on the ground, prototyped on the ground, that we operate from space to get a global picture, to expand our horizons, to go to the moon, to go to Mars. So, I think we talk about space weather the wrong way. You know, just think about it. When we talk about it, the big thing we talk about is the Carrington event. People build still in 100-year floodplains. Why is that? There's a huge body of literature about why people accept unreasonable risks. And we can show, technically, that why this is not a wise decision to ignore the risks of space weather. But the problem is, it takes a long time to explain all of that stuff. You know, hey, let me give you more words, let me give you more numbers. But the psychological obstacles are, you know, temporal discounting. It hasn't happened, you know, it's in the future. There's, you know, probability is tiny. You know, that nothing's happened recently, or nothing will happen, or, you know, right now nothing's going on, so the future's going to be okay. You know, we're making changes. So people discount these future risks, but they are attuned to profit margins. And I'll tell you, one of the things we need to do is think about, you know, how we reframe the benefits of understanding the space environment so that the merchant princes realize that, yes, we're not going to save, we're not going to save civilization, but we may save you even just 1% of your expenses. You'll have 1% greater profits. You say, 1%? Wait a second. If I have a $1 trillion space economy, now we're talking money. So again, and 1% is an extremely low case, just to give you an idea. All right, so just a couple more things. So one of the things, we're challenged by, this reminds me of a story on a trip to San Francisco, where, I saw a guy standing on a bridge. He looked like he was going to jump off. Remember what the left hand means? It's sort of a joke, okay? So, and I said to him, hey, don't do it. He says, nobody loves me. I said, well, God loves you. Do you believe in God? He said, well, yes. And I said, well, are you a Christian or Jew? He said, a Christian. Me too. Protestant or Catholic? He said, Protestant. Me too. What franchise? Baptist? Me too. Northern or Southern Baptist? He said, Northern Baptist. Me too. Northern Conservative Baptist or Northern Liberal Baptist? Northern Conservative Baptist. Me too. Northern Conservative Baptist, Great Lakes region. Northern Conservative Baptist, Eastern region. Northern Conservative Baptist, Great Lakes region. Me too. Northern Conservative Baptist, Great Lakes region, Council of 1879, or Northern Conservative Baptist, Great Lakes region, Council of 1912. He said, Northern Conservative Baptist, Great Lakes region, Council of 1912. So, die, heretic! And they pushed him over. So, think about that. We do that all the time. We look for the tiny differences. So, dynamic was selected. I was on a dynamic team. My dynamic team lost. Others in the audience are on dynamic teams that lost. There are other people in the audience, the dynamic teams were selected. That is the hero's journey. It took 15 years. So if you would do me a favor, could you all applaud the selection of Daphne and the efforts of all those teams, all the people, including my buddy Jens. We started in 2011 on this journey to get dynamic to the point where it's going to fly eventually, we hope. So let's applaud, let's say. And I don't see Amy here, but I do see Scott. Scott, thank you very much for leading that effort. I thank Tomoko and thank Amy for doing that. So, this is a huge effort, right? We ended up with this mission to study space weather impacts on the Earth. And the thing I want you to remind you of is that this is an opportunity to practice the abundance mindset. Don't be critical of GDC Trailblazer, or Dynamic. The reason is that's a done deal. All you can do is ruin it for the community. What we need is to get behind it. Like I said, I'm a loser, right? But I still think we really need to get behind Dynamic as selected, Daphne. We need to get behind Trailblazer. We are focused on the tiny details. There are things that will be done, and we want to see both of those missions succeed, because even though you are not maybe directly connected to these missions, imagine what we call budget pressure. If all the people that are connected to dynamic and dynamic science all of a sudden start trying to get money, that's the scarcity mindset, that's your money, you're going to have trouble. So it's in your best interest to support dynamic fully. And I'll tell you one more thing. What I worry about is, of course, that other people in other communities will seize upon differences in our community, in the ITM community. They will say, hey, look, I talked to so-and-so who's an expert on this, and they say the chosen dynamic sucks. It won't do what they say, and that gains currency at headquarters. Headquarters says, oh, these ITM guys, they can never get their act together. We try and we try and we try, and all they do is criticize each other. But when I go to the solar community, or I go to the MAG community, or the heliosphere community, they're all like, yes, the greatest mission in all time. We want to look for the sun from the top, the bottom, the left, the right, the front, the back. You know, that's $2 billion at least. Sure, let's do it. Everybody's in favor of it. So I'm not saying to be dishonest. I'm saying be true to yourself, but exercise emotional control. It is tremendously disappointing to lose. But for the good of us, for the community, and for yourself, you need to move on. And there are other opportunities. So let's summarize. I could see everybody's getting nervous. Too bad. So if you stay focused on why has my world changed, where's the stable funding, you know, then your mindset will focus on scarcity. You'll react from fear. You'll be angry. You'll be anxious. If you shift to where are the problems that must be solved, what can I do to bring value regardless of agencies? And there are lots of funding sources. I get money from DHS. I get money from lots of other places. I get a little bit of money from NASA. I get a little bit of money from NSF. You know, there's all kinds of places. Make the adjustment that your academic work does not constrain you. Your academic work prepares you. Your work provides the foundation for new branches. Be the oak. Think about it as a growth opportunity and open your scope of action. Now, I'm not saying that any of this is easy, but no hero's journey is ever easy. It's hard. But if you want to be the hero of your own life, you have to do the hard things. We do these things not because they are easy, but because they are hard. Who said that? John F. Kennedy. Scott knows. So, your institutions will be looking for new options. If you talk to deans, if you talk to the trustees at a university, they don't care about science. They care about money. Notice the left arm's not raised, not a joke. So use your ecosystem, use where you are, and understand their value system to achieve the goals you want. So I want to issue a sincere thank you, and hopefully Nate is walking slow, because I only have one more thing I want to say. Keep walking slow. One of my favorite books, one of my favorite quotes. When I was young, I had to choose between the life of being and the life of doing. And I leapt at the latter, like a trout to a fly. But each deed you do, each act, binds you to itself and its consequences, and makes you act again and again. Then seldom do you come upon a space, a time like this between act and act, when you may stop and simply be, or wonder who you are. And that is what I'm profoundly grateful to, because it helped me organize my thoughts, the things I've learned over the years that I've tried to share with people. I hope this was both entertaining and ultimately valuable to you. I could have talked all about all the great things I did, but, you know, not even I'm interested in that, you know. So, all right. So thank you very much. I really appreciate it.
Thank you so much, Larry. I found that personally very inspirational. Do we have any questions? We do. You can't get away yet. There's a microphone that is coming around.
Thanks, Larry. That was very inspiring in a way.
In a way.
Yeah, and I appreciate your optimism about, and your point about being adaptable and looking for new opportunities in a time of scarcity. But I think that all that different money that is sloshing around that you talked about, a lot of that is only going to benefit the military-industrial complex and AI-obsessed billionaires. And a lot of us got into this career to not have anything to do with that. And I think maybe we should push back while we're also being adaptable and flexible and trying to make our careers go forward. We should push back on Joe Westlake's vision. We should push back on only funneling all of our resources towards that end. And I want to know your thoughts on that.
Okay, so I certainly respect and appreciate your point of view. What I would say is that I'm not saying you should compromise your values, say that you should be conscious of the choices you make. That's part of it. But the thing is, you don't have to say do work that's classified. What I'm saying is that if you think about what it is that people need, cast what you do in terms of that they will understand. Make the effort so that, that an example would be, think, if you are, AI, everybody's talking about AI. All right, so what's one of the things right now that's going on? AI is being used to do weather forecasting. Are there any physical models in the AI? No. It's just looking at meteorological data. So what if you said, hey, let's just pretend I'm making something up. That's on the spur of the moment, so it's not real thought out. And what we would do is, talk back and forth and figure out how to do it, where would be the sponsors. But you could say, what I want to do is I want to understand this, because this is really important. The physics is complicated, very complicated. What I'm going to do is try an AI model to see if I can capture the behavior, because the tech bros, they want to have actionable information for, say, orbital dynamics. They want to know where I'm going to be at a particular time, what the probability of a collision is. And right now, there are roughly 10,000 collision warnings issued per day in the community, and that is not actionable. So what you want to do, so the driver for them is, I want to have a good thing, and you say, hey, I thought of AI, here's something that's new, here's what I'm going to do. Now, in order to do that, I have to figure out this, this, and this. But there's where I want to go. That's the value statement, and I'm going to use AI to do that. Another way might be, okay, let's talk about a big thing that people are worried about right now. This is a little bit more onto the magnetosphere community, is high altitude nuclear explosions. Really sort of way over in the DoD part. Well, there's all kinds of talk about remediation. How do you deplete the radiation belts? So that means you have to understand the radiation belts. Are there ways to do that? Can you think about that? You don't have to do classified research to do that. You can say, hey, here's something, here's my idea, here's what that Heilmeyer catechism, here's where we're going. This is what we want to do. Here's the steps we have to take. Here's the investment you need to make. So those are the kind of things that you would have to work on it. This is all just off the top of my head, things that you could do. But I certainly respect your viewpoint, and that's not an uncommon one. And it is, it is what it is.
Okay, we'll take one more question from Zin Xiao, and then as we're doing that, we're all going to connect this other laptop here.
Larry, thank you so much for sharing your wisdom with the community. You reminded me how I met you the first time. More than 25 years ago,
Well, you mistook me for Jim Russell.
Exactly.
That's the only
I
reason you've talked
mistook
to
you
me,
as
because he
Jim
said-
Russell because
I think what I remember
two
is
Asians' eyes, he and Jim Russell somehow look the same to me. Many years ago. And then
what you said, I remember was, you're not Jim Russell. I don't want to talk to you.
No.
sounds
Then less
okay,
than
sorry, that was
20
my-
years ago,
that's a joke.
not long after I moved to Boulder, you gave a talk at a conference in Boulder. And when people ask you, how are your new results compared with some previous mission results, you gave a very famous phrase, identical except differences. And I remember I heard Dick Goldenberg said, Dick, you and I are identical except differences. Because we were all made, our body made 70% of water. Yeah, so I have a question
Nate's pushing me off the edge here.
Yeah. I have a question to you. To me, there are ups and downs. So my advice to people say, don't be a quitter. Don't quit.
Yes.
Be a fighter, fighting through. So even if the cheese has been moved, so what? Go to find new cheese. How do you think about it?
And what word would you use to describe that? Heroic, right?
And with
That's
that,
the hero's journey.
well, we are
Okay,
thank you. One more round of applause for Larry. Thank you, Zin Xiao. And I really quickly, Dr. Waldrop with her very fancy movie.
Well, see, now it's all built up, and I'm going to feel bad if you don't like it, but it's also hard to follow that tour de force. Thank you very much, Larry, for a great talk. Oh, we're doing, yes. Okay, so super fast. Thanks everyone for indulging me. I was really excited about these movies. So I'm gonna play it. It's gonna be really quick. What you're gonna see is, here's the storm. There's the aurora. Did you see them pop up at the end? That's incredible. This is the first storm we saw with the camera turned on. We've got 3 other storms that we're still waiting to analyze. But this is what I meant about the auroral oval. Here's the moon peeking in. But the fireworks happen in the change in radiance image. So here it comes. And did you see it grow up out of the exosphere? That's 30-minute cadence here to step through until it becomes, and it starts to fill the exosphere. Now, unfortunately, we slewed away, so we don't know if it keeps expanding, what happens at the end of it, immediately after this frame. But stay tuned, lots going on. And please reach out if you want to coordinate on any sort of data analysis, modeling, data model comparisons. We're really, really excited to have this data in hand. Thanks very much for indulging me on this.
Thank you so much, Laura. Thank you, Larry. Please enjoy your coffee.